Hi everyone. Today we are going to discuss about conductance. First we are going to discuss electrolytic conductance. Flow of electricity through solutions of electrolytes is due to the migration of ions when a potential difference is applied between the two electrodes. That means when we are applying a potential difference between two electrodes, the ions of the electrolytes, that means the electrolyte contain cations and anions. We know cations are positively charged and this positively charged cations moves towards negatively charged electrode known as cathode, and the negatively charged ions are known as anions, and these anions moves towards positively charged electrodes known as anode. This movement of ions produces electricity. The ease with which electricity flows through a solution is known as electrolytic conductance, and it is denoted as G or C, or electrolytic conductance, or simply conductance is the reciprocal of resistance. Hence we can represent G is equal to 1 by R. We know the unit of resistance is ohm. Hence the unit of conductance G is ohm raised to minus 1. Ohm raised to minus 1 becomes mho, or in SI system it becomes Siemens. Siemens is represented in S. Next topic, specific conductance or conductivity. Specific conductance is the reciprocal of specific resistance. Then what is specific resistance? We know that the resistance of a conductor is directly proportional to the length of the conductor and inversely proportional to the area of cross section of the conductor. So R becomes equal to rho L by A. Here the constant rho is known as specific resistance. On rearranging this equation, we get 1 by rho is equal to 1 by R into L by A. Here 1 by rho is the reciprocal of the specific resistance. This is known as specific conductance or simply conductivity, kappa. Conductivity is represented by the symbol K, known as kappa, which is equal to G into L by A. We already discussed that reciprocal of resistance is conductance. So specific conductance or conductivity kappa becomes equal to conductance into cell constant. L by A is cell constant. L length of the conductor, A is cross-sectional area of the conductor. When the length of the conductor is 1 centimeter and the area of cross-section is 1 centimeter square, then K becomes equal to G. That means the specific conductance or conductivity is the conductance of the column of unit length and unit area of cross section. The conductivity or specific conductance of an electrolytic solution is defined as the conductance of a column having unit length and unit area of cross section. Here we are represented the length and area in centimeters. We can also represent it in meters. So conductance or specific conductivity, specific conductance or conductivity is the conductance of 1 meter cube of the material or 1 centimeter cube of the material. In SI units, the unit of specific conductance is Siemens per meter or Siemens meter inverse. And in other units, K becomes 1 by R into L by A. 1 by R, the unit of resistance is ohm, then 1 by ohm into unit of length, that is centimeter, and area centimeter square. Hence the unit become ohm raised to minus 1 centimeter inverse or ohm inverse centimeter inverse. This specific conductance or conductivity is the property for characterizing metallic conductance. Another one is equivalent conductance. Equivalent conductance is represented as lambda equivalent. This equivalent conductance of an electrolytic solution is the conducting power of all the ions produced by 1 gram equivalent of the electrolyte in the solution. Conducting power of all the ions produced by 1 gram equivalent of the electrolyte in the solution is known as equivalent conductance. For the explanation, we are considering two electrodes, negatively charged electrode and positively charged electrode. These two electrodes are separated by a distance L. This L become 1 meter or 1 centimeter, unit length apart. The electrodes are unit centimeter or unit distance apart. And the area of cross section of electrode plates are unit meter square or unit centimeter square. And the electrolytic solution is filled in between these two electrodes. Hence, the volume of electrolytic solution is 1 meter cube. We have already discussed that the conductance of 1 meter cube of solution is known as specific conductance. Okay, in this case, this 1 meter cube of solution contains 1 gram equivalent of the electrolyte. Then, in this case, the conductance which is equal to specific conductance. Why the conductance become equal to specific conductance? Here, it is the conductance of 1 meter cube of the solution. 1 meter cube of the conductance of 1 meter cube of the solution is known as specific conductance. And this solution contains 1 gram equivalent of the electrolyte. The conducting power of all the ions produced by 1 gram equivalent of electrolyte is known as equivalent conductance. Hence, here the conductance equal to specific conductance equal to equivalent conductance. Suppose we are diluting this solution 1000 times. That means here the volume of solution becomes 1000 meter cube. Then what becomes the specific conductance? The specific conductance become 1000 times increased. So simply the equivalent conductance, but on dilution also the number of gram equivalents will not change. This solution contains 1 gram equivalent of the electrolyte. So the equivalent conductance equal to the volume into specific conductance, K into V, or it can be, the volume can be replaced by concentration. So lambda equivalent becomes equal to K by C. The unit of lambda equivalent, we know that the unit of specific conductance kappa is equal to Siemens per meter. So Siemens meter inverse. And the concentration, here the concentration is represented as equivalents per meter cube or equivalent meter raised to minus 3. Hence the units become Siemens meter square equivalent raised to minus 2. This is the SI unit of lambda or equivalent conductance. When the concentration is replaced by normality, normality is represented as N. Here the normality of solution is the normality means gram equivalent per liter. Hence the unit become ohm raised to minus 1 centimeter square equivalent raised to minus 1. So lambda equivalent equal to K into V, specific conductance into volume. Or this equation can be represented in many other form. Another one is lambda equivalent is equal to K by C, and other expression is lambda equivalent is equal to K into 1000 by N. Another one is molar conductance. Molar conductance is the conducting power of all the ions produced by 1 gram mole of electrolyte in solution. The conducting power of all the ions produced by 1 gram mole of the electrolyte in solution. The only difference between equivalent conductance and molar conductance is that in equivalent conductance, the equivalent conductance is the conducting power of all the ions produced by 1 gram equivalent of the electrolyte. But in the molar conductance, molar conductance is the conducting power of all the ions produced by 1 gram mole of the electrolyte. Here also the molar conductance lambda m is equal to K into V or K by C. The unit is Siemens meter square mole raised to minus 1 as shown in equivalent conductance. The only difference is that in equivalent conductance, Siemens meter square equivalent raised to minus 1. Why it become equivalent raised to minus 1? The equivalent conductance is the conducting power of gram equivalent of electrolyte. But in molar conductance, it is gram mole, conducting power of gram mole of electrolyte. So, the unit of equivalent conductance is Siemens meter square equivalent raised to minus 1. But the unit of molar conductance is Siemens meter square mole inverse. If the concentration is replaced by molarity, then molarity means mole per liter. So the unit become lambda m, or unit of molar conductance become ohm raised to minus 1 centimeter square mole inverse. But in SI system, the unit is Siemens meter square mole inverse. Then we are going to discuss the relationship between equivalent conductance and molar conductance. Here we have seen the relationship between specific conductance and equivalent conductance. Here the relationship between molar conductance and specific conductance. Okay. Then we are going to discuss about the relationship between equivalent conductance and molar conductance. The expression for equivalent conductance in terms of normality is that K into 1000 by N. The expression for molar conductance in terms of molarity is K into 1000 by M. Hence, lambda equivalent conductance by molar conductance equal to K into 1000 by N divided by K into 1000 by M. So, we know that K into 1000 and K into 1000 get cancelled and the expression become M by N or molarity by normality. So, on rearranging we get equivalent conductance equal to molarity of the solution divided by normality of the solution into molar conductance. Okay. We know that molarity is equal to mass per liter divided by molecular mass. Molarity is equal to mass per liter divided by molecular mass, and normality is equal to mass per liter by equivalent mass. So, we substituted this expression for molarity and normality. So, lambda equivalent becomes, or equivalent conductance become equal to equivalent mass divided by molecular mass into molar conductivity. Here, for molarity, we are substituting mass per liter by molecular mass, and for normality, mass per liter by equivalent mass. Mass per liter get cancelled and the expression become equivalent conductance equal to equivalent mass by molecular mass into molar conductivity. These are all about the conductance. Electrolytic conductance means electrolytic conductance is the easiness with which electricity flows through a solution. That is represented as G. That is the reciprocal of resistance. And specific conductance is the reciprocal of specific resistance. That is kappa. Again, equivalent conductance is the conducting power of 1 gram equivalent of electrolyte. Molar conductance is the conducting power of all the ions produced by 1 gram mole of the electrolyte. And these are the relationship between equivalent conductance and molar conductance. Equivalent conductance is equal to molarity by normality into molar conductance, or the equivalent conductance equal to equivalent mass divided by molecular mass into molar conductivity. Okay, thank you.